So before moving on to question 2, let us have a look at this, which I skipped out. So we're stating one condition under which the equation in B applies to the motion of a spherical object, right? So the equation in part B that we're referring to, right, is generally our FD is equal to 6 pi r eta V. So looking at one condition, right, in which this is applicable. Alrighty, go ahead. So how is this applicable? I'm not sure if I explicitly stated it when I was going through it, but this equation only applies, right? So it really only applies so it only applies when what? The object go ahead. Yeah. It will. I mean, okay, so yes, it's only applicable when the object is moving in a fluid, right? But when it's moving specifically at a low velocity. In that fluid. Ready? So it keeps, there is something called Reynolds number, but I don't think we look at it in Cape, right? But when the velocity is low, technically Reynolds number is low, right? Ensuring repeat. Hey teacher, wait, wait, Reynolds number was mentioned? That's what you're saying? Oh, hmm. Alright, hold on. Let's just finish this, right? Ensuring that always you know Stokes' law is valid. Alright, so I'm not sure if there's a specific position you might need to be in the Felicia, but Jano, never really heard what you said a while ago. I'm not sure if you'd like to type in the chat. Basically, you're referring to something about that viscosity thing. Alright, so let me check what you have. So you remember it in unit 2? Reynolds number? I mean, probably. But yeah, so I mean, I don't think I would mention it in unit 1 specifically. Probably after you finish unit 1. The regular thing is that when you finish unit 1, you do unit 2. So when you finish unit 1, you're probably going to remember all of velocity, all of terminal velocity and stuff like that. And then we can just add in Reynolds number there because you already understand the concept. So I don't want to put too much one time. But yeah. Alrighty, so it probably is in unit 2. Let's move on. The terminal velocity Vt of the metal sphere is given by the equation here, right? Where K is a temperature dependent constant that determines the resistance to motion in the fluid or of the fluid. So everybody would know that generally that K is eta. That's literally what K is. I don't know why they did this to the question. It's rather dumb. But okay. So what are we doing here now? What would be the units of K? Anyone? Alright, first of all, let's transpose to find K, right? At the end of the day, right, we would have K being equal to what? Mg over 6 pi Vt R. Alrighty, so if we transpose there, right, we just swap around the variables, right, to be very honest. So we have that there. Mass is in kilo. Wait, first of all, you guys understand what I just did, right? Okay, so not entirely, that's fine. So what we did, right, was basically times both sides by K, right? And then we divided both sides by Vt. So we ended up moving the K to one side and then pushing the Vt to the other side. Alrighty? So if we multiply both sides by K, we're going to get Vt K is equal to mg over 6 pi r. The pi looks very weird, pi r, right? And then we divide by the Vt, you know, right? So this is literally multiplying by 1 over Vt, right? And we, okay, all right, that's fine. Okay, so we have that there, right? So some little dimensional analysis, mass, the SI unit for mass is kilograms. Alrighty? The SI unit for G is what? G is what, guys? And acceleration, what is the unit of acceleration? Lovely. Divide all of this by 6 pi has no units, we don't care about it, couldn't care less, right? Terminal velocity, velocity is what? Meters per second, lovely. And we times that by what? R is radius, and radius is in what are the units of K? Cancel, cancel. Kilogram per meter. Does this make sense? Hold on, this is squared. There's a squared here. Second is actually squared. So if we look at it, it's going to literally be, hold on. There's a squared here, so can't be this, can't be this. So there's a meters per second, there's a meters per second squared. So what would the true value be? What would cancel to give what? So it's a kilogram second per meter. You wouldn't be kilogram second per meter. This is going to be that. We'll cancel that upon that. It's going to be kilogram per second per meter. Alright? Because what's happening with the meters per second squared and the meters per second specifically, you know, is that we're going to end up with 1 over s, right, which is represented as that. That is the unit. Hopefully you guys understand what I'm saying. Because you have per second times per second squared, which is just literally this, or which is like divided. So hold on, let me remove these. you end up with something kind of like this divided by that. These would cancel, leaving 1 per second up top, and that is represented as that. Does that make a little bit more sense? Alrighty, so hopefully if there's a question you can ask. Alrighty. But what I was saying here, is that I'm not too sure if Cape just expects you to know what's happening here. But based on the equation above, we do not have the terminal velocity, therefore we cannot answer the question, right? If there's anybody that points out that, oh, you can still answer the question, right? I really don't know. Because you have M here, you have your R. You also have, well, that is M and R, right? We know the value for K specific. We don't know the value for K. We have 6 pi, right? So the only unknowns that we have here is K and VT. You can't really solve with 2 unknowns like this. Already? So I said to assume VT being 0.2 meters per second, and we'll do the question using this value for practice, because I didn't see a way to do this question if we didn't have one variable like that. I tried solving it simultaneously, and that just led me to going back to my assignments because I was like, I'm not being paid enough to solve this simultaneously, right? But we're just looking at this, right? So if we use VT as that, right, what the entire question is just asking us now to do is just plug in all the values, right, and get an answer. You guys understand what I'm saying? Alrighty. So if you found a way to solve it without having one of the variables now, be my guest. Alright. Not saying it's impossible. I think it's most definitely impossible. Right? Probably there was something missing from the paper. So, or probably how I copied it, there was something missing, but there will be no issue. If on the paper it gives you the variable, then you should be able to work it anyway. 9.81, and this will be meters per second squared rather. Just plugging in the values. We have M, we have G, and then we have 6 pi times the 0.2 meters per second, which I placed up there, right? And we're timesing that by 1 times 10 to the negative third meters, right? How we end up getting now, K is going to be equal now to what? Right, so K is going to be equal to roughly, right, the numerator is going to be roughly 4.905 times 10 to the negative second kilogram meters per second squared, right, divided by the denominator, which is roughly 3.7699, right, times 10 to the negative third power meters. And then that brings us to a value which is roughly 12.99 kilogram per second per meter. Alright, so what we're saying that the value of K in glycerin at 30 degrees Celsius, right, is roughly 13 kilogram per second per meter, right? So that's what we're saying. Is this clear, everyone? Alrighty, let's move on. So we're headed into, we answer the questions on this page already. So we're heading into the question number 2, which should be a lot more fun. Alrighty. So give it a minute. So we're asked now to differentiate between precision and accuracy. What is precision and what is accuracy? Anybody? Yes, I am. Lovely. That is exactly what it is. I think somebody raised their hand. All right. I'm not sure if it was you, but if it's not you, could they go ahead as well to let me know what their definition was? All right. So I don't know if it's going to be a waste of time for me to write it though. But precision specifically, it has to do. I'm not gonna write the full thing, right? It has to do with consistency and repeatability, right? Of measurements, regardless of their accuracy. So we're looking at consistency. And the fact that it may be repeatable. So repeatability, right? And we're saying that accuracy now. What does accuracy speak to? We're saying how close it is to the true value. So accuracy is really and truly just the closeness, or yeah, close to the true value. Right, so that's all we're looking at. 2 marks, right? So if we know what those are, right, what do we have here? We must comment on the accuracy of the results in the table. Go ahead, person who raised their hand. Yeah, go ahead. Repeat. The true value. The true value is right here. All right, lovely. Right, so we're saying that the accuracy, right? Okay, so based on the numbers, right, they are not close to the true density, right, of 3.75 grams per milliliter. Therefore, it is low accuracy. Right? This is low accuracy, right? What can we say about the precision of the experiment specifically, though? Hold on. We're saying precision, and you answer the question by saying it has high accuracy? Can't answer that. Rephrase. Are precise. The difference is 0.02 though. What? Oh, there. Oh, sorry about that. I mean, it's in the ballpark of 0.02, 0.01. Okay, so they were saying that the measurements in this group are they're closely grouped, therefore they are precise. But because they are far away from the true value, they are inaccurate. Alrighty? So that's basically what we're talking about there. So what this one is saying is low accuracy. Right? And this is now it's saying but that's high precision. Right? Hopefully everybody understood all of that. Ready? Next thing. My bad. Wait, hold on. There's a question missing? Or is a question up here? Alright. The following formula is used to calculate the centripetal force of an object undergoing circular motion. The centripetal force is equal to the mass times velocity squared divided by the radius. Alrighty? Or the radius of the circular path. Write an equation to determine the fractional error of F, given that the fractional error in M, V, and R are given the fractional error of M, V, and R. How will we find the fractional error again? Go ahead. You can answer the question. Mm-hmm. Mm-hmm. That's an okay. All right. So we have delta. So as you're saying, right? So delta m over m. My bad. Right, and we're timesing it by 2 times delta v. What are you saying? Mm-hmm. Okay. Alright, so I would prefer delta f over f, but this is fine. Because if I write delta f over f, that's not necessarily giving me delta f. So this would give us delta f truly. Alright, so that's fine. We went through a small session of going through it, uncertainties, and I think it's already posted. But yeah, that is the answer to that question. I want Mark to just provide that little thing. Right, so fractional meaning you write everything as a fraction, right? You write every uncertainty as a fraction, right? With the actual, well, it wouldn't be the actual value, but with the estimated value as the denominator, right? And because v is squared, we take 2 delta v, right? Divide by v, and then that should be it from there on out. Alrighty. We're looking at this now. An experiment is performed using the apparatus in figure 1. A small disk of mass m on a frictional table is attached to one end of a string. The string passes through a hole in the table and an attached narrow, and an attached narrow vertical plastic tube. A disk of mass large M is hung at the other end of the string. One student holding the tube makes the disk rotate in a horizontal circle of constant radius r, while another student measures the period t. Right, so we end up with something like this. This should be fine. Really and truly, this is a one-man job, but it's fine. 2 students, that's okay. We're now asking to state 2 conditions that must be satisfied if a body is moving with uniform circular motion. But there are 2 conditions that we must have. Oh, the thing is skipping. 2 conditions to maintain uniform circular motion. Let's go. Firstly, okay, so let's write that then. So the object, this writing thing is not working, but the object must maintain constant speed. So if you write constant velocity, if I were the marker, I give you 0 marks from the start, right? Because remember, circular motion, direction is changing, velocity will change. If you write constant velocity, no, 0 marks, right? So it's constant speed that the object has. Alrighty. Next thing, what's the next criteria? Next criterion. The net force acting on the object must be directed to the center of the circular path. Not true. Net force must be directed to the center. Right, so that's what we're looking at, really and truly, right? So in other words, rather, right, the net force must be centripetal, right? It must be directed to the center of the circular path. Show the relationship between, sorry, let me just scroll back up a little bit. So show the relationship between the period t, the radius r, and the masses small m and big M, right? And that is given by the equation t is equal to 2 pi times the square root of small m times r divided by large M times g. We must show this. Show that this is true. Alrighty? Let's start out. Do you guys want me to go through it or what? So what time is it? Alrighty. So the centripetal force on the disk, right? A small disk of mass m, we're saying, is rotating in a horizontal circle of a radius r at a for uniform circular motion, right? We can give the force Fc, right? And Fc is equal to what? M times v squared over r, yes? Where v is the tangential speed of the disk, the tangential velocity. Alrighty? The relationship between the speed and the period now. Since the disk completes one full circular rotation in 2 pi, right, r, right, in time t, we're going to have something else, right? So remember, the entire circle is 2 pi radians. Remember that? The entire circle is 2 pi radians. So by virtue of the relationship between the speed and the period, can anybody tell me what a period is? What is a period? Not a frequent, it could be in terms of frequency. So what would you say in terms of frequency? The period t is how long it takes to complete one oscillation or one rotation, right? So we could say now the relationship between the speed now is going to be 2 pi times the radius, because 2 pi is the entire circumference of the circle, 2 pi, right? R there, right, divided by t. That is the relationship between this tangential speed and the period. Okay, now we can substitute to find our answer. That's all we do now. Substitute, and we're on our merry way. Alrighty, so let's substitute. So Fc now, I don't know if I'm going to have enough space, but we're going to do it either way, right? Is equal to m times 2 pi r. Let me just use common r. I don't want to use a capital R. Give me a second, let me fix this. R, right, over t squared divided by r, right? And that's going to be equal to what now? M times 4 pi squared r squared divided by t squared r. Are we following? Alright, so this is now equal to what? Some things cancel, not true? we're going to have cancelling occurring. What's going to happen? We're going to end up now rearranging neatly to put the m in. Right, we have 4 pi m, right, r divided by t squared. Because the r's cancel. One of the r cancel up there, one of the r cancel up there, leaving one there. Alrighty. Now we have to balance the forces now. Recall now that Fc is equal to mg. Not true. Therefore, we can look at the fact now. From that now, we show now that 4 pi mr divided by t squared, let me write the r properly, right, is equal to large mg. Tell me if you're getting lost, right? Let's draw a line down the center so we can continue on the other side. Right? Rearrange now. We must transpose to isolate t, right? Because it's t we have on the left hand side. So let's keep t on the left hand side now, right? So we end up now with t squared being equal to what? 4 pi squared, right? mr over mg. Alrighty, take the square root now. T is equal to now 2 pi, right, times the square root of mr over mg, large M g. And that is exactly what we asked for. This is the answer. It's the same as this. These are the same. Is that fine?